Hello everyone. This is the second session of the morning. Our next speaker is Professor Sudesh Kaur Khanduja from xn+axm+b, and she's going to talk about when is z theta integrally closed. Yes, Khanduja.
Echo is because of two devices.
Yeah, one has to be. Hello, Professor Khanduja. Your mic is muted.
हाँ, अब फिर से शेयर करूं व्यू में जाके ना हाँ
Reason for the echo.
शेयर स्क्रीन हो गया ना लो चलो शेयर स्क्रीन कर दिया अब आ गया जी आ गया हाँ अब हो रहा है ठीक है नहीं आ रही नहीं हो रही वो ऊपर व्यू नहीं दिख रहा मुझे वो व्यू करने से आएगा हाँ
You are able to see that. Madam, you can start actually.
हो गया बस
We are visible, madam, for us. You can start. Your screen is visible.
ठीक है madam, everything is fine. You can start your lecture now.
Okay, thank you, Krishnendu. Good
So
morning.
chair, the chair. Let you introduce the chair. Chair कौन है भाई?
Krishnendu, Professor Krishnendu.
Okay. So I think Siddharth was supposed to be the chair, but anyway, so it's a pleasure to.
We started.
Yeah.
Krishnendu, I am the chair.
You are the chair. Okay. Go ahead.
Yeah. Okay. Yeah, I probably is not visible. Yeah. Okay. Let's begin the talk.
Thank you and good morning to all participants in India and Asia, and good afternoon to participants from Europe, and late good evening to friends from USA. The title of my talk is when is Z theta this ring integrally closed? And these are my two affiliations, Punjab University Department of Mathematics and ISER Mohali main gate. That shows the main gate of ISER Mohali. Now for some notations, we begin with some simple notations. For an algebraic number field K, AK will denote its ring of algebraic integers and DK its discriminant. And some basic facts: AK is an integrally closed domain with quotient field K. AK is a free abelian group of rank equal to the degree of K over the field of rational numbers. Next, any Z basis of AK is called an integral basis of K. Another fact, an algebraic number field K of degree n is called monogenic. If AK equal to Z theta for some element theta of K, that is 1 theta raised by n minus 1 is an integral basis of K. Such an integral basis of K is called a power integral basis, or more briefly a power basis of K. Next, a monic irreducible polynomial fx belongs to zx of degree n having a root theta in complex numbers is said to be monogenic if 1 theta raised by n minus 1 is an integral basis of the field q theta. Next result, when k equal to q theta with theta an algebraic integer having minimal polynomial fx over q, then the discriminant of the polynomial fx and the discriminant dk of the field k are related by a simple formula. Discriminant of fx equal to ak is to z theta whole square, that is the index of ak is to z theta stands for the index of the subgroup z theta in ak multiplied by dk. The group index of z theta in ak is called the index of theta or the index of fx. And another simple basic result is, given an algebraic number field k equal to q theta with theta and algebraic integer, an important problem in algebraic number theory is to verify whether ak is equal to z theta or not. And in this direction, in 1977, Uchida proved the following theorem. Let k equal to q theta with theta in ak having minimal polynomial fx over q, then ak equal to z theta if and only if fx does not belong to m square for any maximal ideal m of the polynomial ring zx. And not only that, in a simple lemma, he described all maximal ideals which contain a monic polynomial, an ideal m of zx of the polynomial ring zx which contains a monic polynomial is maximal if and only if the ideal m is of the type p comma gx for some prime number p, if and only if m is generated by p comma gx for some prime number p and a monic polynomial gx belonging to zx which is irreducible modulo p. So, after reading Uchida's paper and my student Jhorar in 2015 proved the following simple result. Let k equal to q theta be an algebraic number field with theta in the ring ak of algebraic integers of k having minimal polynomial fx equal to x raised by n plus ax plus b over the field q of rational numbers. Then ak equal to z theta if and only for each prime p dividing the discriminant d equal to -1 raised plus -1 b raised by n -1 n to the power n plus a raised by n -1 raised by n of fx. One of the following conditions is satisfied. Number one, when p divides both a and b, then p square does not divide b. And number two, when p does not divide ab, then p square does not divide the discriminant d of fx. 3, when p divides a and p does not divide b, with k as the largest power of p dividing with k as the largest power of p dividing a, then either p square divides a and p does not divide b1, or p square does not divide a and p does not divide this expression where a2 equal to a over p and b1 equal to minus b to the power p to the power k plus p over p. When p does not divide a and p divides b with l as the largest power of p dividing n, then either p divides a1 or p square does not divide b, or p does not divide a1 and p does not divide this quantity where b2 is b over p and a1 is minus a to the power p to the power l plus a over p. So she gave explicit, necessary and sufficient conditions for ak to be equal to z theta when theta is a root of an irreducible trinomial in which the second term has degree 1. Keeping in mind the well-known result due to Selmer that the polynomial x raised by n minus x minus 1 is irreducible over rationals for all n, the following is a quick application of theorem 1.1. Let k equal to q theta with theta a root of the polynomial x raised by n minus x minus 1, then ak equal to z theta if and only if n to the power n minus 1 minus n raised by n minus 1 is square free. And another corollary she obtained is the following. Let k equal to q theta with theta a root of the polynomial x raised by n minus b belonging to zx, that is k equal to q theta is a pure extension of degree n of Q, then AK equal to Z theta if and only B is carefree. And for each prime P dividing and P square does not divide B raised by P minus P. Now, of course, it is but natural to extend this result to all irreducible trinomials over Z. For that, one needs the explicit calculation of the discriminant of a trinomial, and this explicit calculation was given by Swan in 1962. Swan has shown in one of the papers d equal to plus minus 1 b raised by m minus 1 b to the power n1 minus m1 n to the power n1 minus 1 to the power n1 a to the power n1 m to the power n1 n minus 1 raised by n1 minus m1, where denote is a GCD of m and n1 equal to n upon denote, m1 equal to m upon denote. This expression, by the way, is very simple to calculate the discriminant of x to the power n plus ax plus b, but it takes a bit of effort to calculate this discriminant of a general trinomial. So, characterization of primes dividing the index of a trinomial. So, for general trinomials, irreducible trinomials, this question was taken by Jakhar and Sangwan, my PhD students in ISER Mohali in 2017. Let k equal to q theta with theta an algebraic integer having minimal polynomial, a trinomial x to the power n plus a x to the power n plus b of degree n over q, and we denote the GCD of m and n by denote, and we define m1 equal to m over denote, n1 equal to n over denote. Then they prove that a prime factor p of the discriminant d of fx does not divide ak to z theta if and only if p satisfies one of the following conditions. So not only they prove that ak equal to z theta, they prove something more general, that they characterize all those primes which divide ak's to z theta. And of course, any prime which divides ak's to z theta in view of the formula that discriminant of the polynomial, discriminant capital D is equal to the index of ak's to z theta whole square multiplied by the discriminant of the field k. So any prime which divides the index must divide the discriminant. So a prime p of the discriminant, a prime factor p of the discriminant d of fx does not divide the index of theta if and only this the index ak to z theta. Number theorists call it the index of theta by abuse of language, if and or for the sake of brevity, if and only p satisfies one of the following conditions. Number one, when p divides a and p divides b, then p square does not divide b. When p divides a and p does not divide b, and the highest vpn stands for the highest power of p dividing the number n. This is j greater than equal to 1, then either p divides a2 and p does not divide a2 multiplied by this expression, where a2 is a1 a by p and b1 is 1 over p b plus minus b to the power p to the power j. And similarly, in the other case, when p does not divide a and p divides b, then since p divides the discriminant, looking at the formula of Swan, we see that vp of n minus m equal to L greater than 0, then either p divides a1 and p does not divide b2, or p does not divide this expression. A1 is given by this and a2 is given by this. And when p does not divide ab, p divides m with n equal to s dash p to the power k, m equal to s p to the power k. P does not divide the GCD of s dash and m, because once p does not divide ab and p divides m, then by the formula of Swan, one can see that p will divide n automatically. So with p not dividing GCD of s dash s, then the polynomials x to the power s dash plus a x to the power s plus b and 1 over p a x s p to the power k plus b plus minus ax to the power a into x to the power s minus b p to the power k. By the way, the polynomial inside the bracket has coefficients multiple of p, and therefore when we divide by 1 over p after the quotient after this division, the polynomials still have coefficients. These are co-prime modulo p. And similarly, the last condition, when p does not divide abm, then p square does not divide c minus e, where c and e are the expressions in the, where c minus e is the expression in the middle term of c minus e is here. This is expression c, and this is the expression e, the discriminant of the trinomial x to the power n plus e x to the power n plus b. So they gave these necessary and sufficient conditions for a prime p. P does not divide the index of theta if and only in all the cases they describe necessary and sufficient condition. So this is Jakhar. He is now a faculty at IIT Bhilai, and he is a faculty in LM Lakshmi Narayan Mittal Institute of Technology.
मैडम दूसरा ही फोटो दिख रहा है मैडम,
हाँ?
आपके प्रेजेंटेशन में दूसरा ही फोटो दिख रहा है.
अच्छा, कौन सा सर? ये अनु जाखड़, दिस इज नीरज, एंड ये तो मैं हूँ. And this is my office in ISER Mohali.
Okay.
So
प्रेजेंटेशन अभी दिख रहा है प्रेजेंटेशन.
So there's a small application of interesting application. Consider fx equal to x to the power n plus a x to the power n minus 1. This is irreducible over q, but parent criterion, which states that if a naught is not equal to 0 and you consider the constant term of polynomial with integral coefficients is non-zero, and mod of the second term is strictly greater than 1 plus absolute value of other coefficients, of course leaving the leading coefficient 1, then px is irreducible over the field Q of rational numbers. Note that if p is any prime dividing the discriminant of the polynomial px, of the polynomial fx, of the trinomial fx, special kind trinomial, and this is irreducible by parent's criterion, because here the second term is mod a, and mod a we have taken to be greater than 1 plus mod a is greater than equal to 3. So so it's irreducible. And note that if p is any prime dividing d and a, then p will not divide a into n minus 1, because we have taken a to be co-prime to n. So by the theorem of Jakhar and Sangwan, ak equal to z theta if and only if the discriminant is square free, and one can check by simple calculation that d and a is square free when n equal to 3 and a equal to plus minus 1 plus minus 2 plus minus 4. And for larger n and larger a, we didn't care to check because the calculation went very. This is a parent who proved the interesting parent criterion. Now comes it is also a very interesting one of the important problems in algebraic number theory, that given a rational prime p and given an algebraic number field k, how many prime ideals of ak lie over the prime p. That is how the ideal pak can be written as a product of prime ideals of ak. What is the shape of those prime ideals? What is the residual degree? What is the norm of every prime ideal? And with which power those prime ideals occur in the factorization of PAK. So in this regard, in 1878, Dedekind proved the following theorem on splitting of primes. Let k equal to 2 theta be an algebraic number field with fx as the minimal polynomial of the algebraic integer theta over q. Let p be a prime number. Let f bar x equal to g1 bar x raised by e1 g bar x raised by er be the factorization of f bar x as a product of powers of distinct irreducible polynomials over z mod pz, with each polynomial gix belong to zx monic. suppose that P does not divide the index of the subgroup Z theta in AK, then this is the only hypothesis. Suppose that P does not divide the index of the subgroup Z theta in AK, then PAK can be written as curly P1 to the power E1, curly PR to the power ER, where curly P1, curly PR are distinct prime ideals of AK. Moreover, curly PI is generated as an ideal of AK by P and GI theta, and the norm of the ideal curly PI equals P raised for the degree of the polynomial GIX. For many years, I taught this theorem for many years. Years after year, I always appreciated its beauty, that from the factorization of the minimal polynomial of fx modulo p, one can it tells us how the prime how the ideal PAK splits as a product of prime ideals of AK. So, but I always thought maybe this beautiful result that PAK equal to this much, where R is this number and PIs are generated by like this, and the norm of PI equals this. Maybe all these things hold. Maybe with a weaker hypothesis than Dedekind took. Dedekind took the hypothesis P does not divide the index of the subgroups at theta. And once in the year 2002, my student Kumar proved that Dedekind could not have assumed less, because if all these conditions are satisfied, then P does not. That's if a prime P has factorization like this, and where PIs are distinct prime ideals and PIs are generated by this, and the norm of PI is P is DI, then P does not divide the index of theta. So a reformulation of P does not divide the index of Z theta in AK. So let K equal to Q theta be an algebraic number field with theta an algebraic integer, and Z round bracket P. This round bracket P stands for the ideal PZ generated by P in Z. Denote let this denote the localization of Z at a non-zero prime ideal PZ of Z. It is immediate from Lagrange's theorem for finite groups that if P does not divide the index of Z theta in AK, then AK is contained in the ring ZP theta. The converse assertion also holds, because if P divides the index of the subgroup Z theta in AK, then by Cauchy's theorem for finite groups, the group AK mod Z theta has an element xi plus Z theta of order P, in which case the element xi of AK does not belong to the ring ZP theta. Thus, P does not divide this index if and only if AK is contained in the ring ZP theta, which is same as saying that the integral closure of the ring ZP in K equal to Q theta equals ZP theta. So Munish read the condition P does not divide AKs to Z theta as that the ring ZP theta is integrally equivalent to saying that the ring ZP theta is integrally closed. So in 1878, coming back to Dedekind also gave the same paper, Dedekind also gave a necessary and sufficient criterion to be satisfied by the minimal polynomial fx of theta over q, so that P does not divide the index of the subgroups at theta in AK. And that result came to mean the necessary and sufficient condition is popularly known as Dedekind criterion. Let K equal to Q theta, with theta an algebraic integer having minimal polynomial of x over Q, and P be a prime number if f bar x is equal to g1 bar x is by even, so on gr by x is by r is the factorization of the polynomial f bar of x into product of powers of irreducible distinct irreducible polynomials over z mod pz. And f bar x is the polynomial obtained by replacing each coefficient of fx mod p as a product of powers of distinct irreducible polynomials over z mod pz with gix belong to zx monic. Then P does not divide the index of the subgroup z theta in AK if and only for each I. Either EI is 1, for each I the following condition is satisfied. Either EI happens to be 1, and whenever EI is greater than 1, then GI bar of x does not divide the polynomial m bar of x, where mx is a polynomial defined by 1 over p fx minus product I going from 1 to r GIX raised by EI. As ZP is the, remember that ZP is the valuation ring of the periodic valuation of rationals. I'm going to define what is periodic valuation of rationals. I'm also going to define what is valuation ring, as ZP is the valuation ring of the periodic valuation of rationals. Dedekind Criterion gives a motivation to investigate when is a simple ring extension of a valuation ring integrally closed. So what is a periodic valuation? That was first defined by Hansel in the beginning of 20th century. For a given fixed prime number P, let BP stand for the mapping from the set of non-zero rationals to integers defined as follows. Write any non-zero rational number as a p to the power s m over n, where m and n are integers. Of course, n is positive, and p does not neither divides m nor divides n, and s is positive, negative, or zero. And we can write every non-zero rational number like this, taking the power of p outside from its numerator and denominator. And in this situation, we define Vp of A, the periodic valuation of A to be S. One can easily verify that Vp satisfies the following two properties: Vp of A B equal to Vp of A plus Vp of B, and Vp of A plus B is greater than the minimum of Vp of A and Vp of B. It is natural to set Vp 0 to infinity because every power of P divides 0, and Vp is called the periodic valuation of rational. The ring as the localization of Z at the prime ideal Pz. It consists of all rational numbers such that Vp of A is greater than equal to 0 is called the valuation ring of Vp. And number theorists also use something called curly periodic valuation. So let K be an algebraic number field and curly P be a non-zero prime ideal of OK. Then we denote by V sub curly P the curly periodic valuation of K defined for any non-zero element alpha belonging to AK by V curly P of alpha equal to S, where S is the highest power of curly P dividing the ideal alpha AK. Because AK is it because number theorists say that like in integers, there is unique factorization property in, like in integer ordinary, there is unique factorization property in AK for any algebraic number field K. That is, every non-zero ideal of AK can be uniquely written as a product of powers of prime ideals of AK. So the exact power which occurs in the factorization of the ideal alpha AK, the exact power of curly P which occurs in the factorization of the ideal alpha AK is say S. So Vp of alpha is defined to be S. The valuation ring of Vp, I should not call it here P, the valuation ring of the valuation Vp is the localization of AK at the prime ideal P. Mathematicians never sit on laurels. They always proceed ahead. So, so Krull extended the notion of evaluation to Krull extended the notion of valuation to general fields. So by Krull valuation V of a field K, we mean a mapping V from K onto not Z, but G union infinity, where G is a totally ordered. And for our convenience, additively written, we write it additively. The totally ordered abelian group in which the addition is compatible with the total ordering, such that the following properties are satisfied for all A and B in K. VA is infinity if and only if A is 0. V of AB equal to V of A plus B of B, and V of A plus B is greater than equal to minimum of VA and VB. In the set RV, which consists of all those elements of K for which VA is non-negative, is a subring of K called the valuation ring of V, and this subring has a unique maximal ideal MV, which consists of all those elements of K for which VA is positive, and algebraists call such rings to be local. RV mod MV, it will be a field because MV is a maximal ideal. It's called the residue field of V, and G is called the value group of V. Remember the value group of the periodic valuation for a prime number P, and the value group of the curly periodic valuation for a non-zero prime ideal of AK. They were all Z. Evaluation V is said to be discrete if its value group is cyclic. I mean, it's isomorphic to Z. And number theorists are always interested in discrete valuations. That is valuations whose value groups are cyclic. This is Kurt Hansel who gave us the notion of periodic valuation, and this is W. Krull who generalized it to valuations with arbitrary, totally ordered everything. I will skip the example of a Krull valuation. So let me be Yuri Arshav from Novosibirsk, Russia, who was the director of that institute, and he was a master on valuation theory. He has also written books on valuation theory. So he generalized Dedekind criterion, extended Dedekind criterion to Krull valuations. And so did my student Munish Kumar also. So let V be a Krull valuation of a field K with valuation in RV, residue field RV mod MV, and value group GV. Let L equal to K theta be a finite extension of K with theta integral over RV. For Gx belong to RVX, let G bar x denote the polynomial obtained on replacing each coefficient of Gx by its image and the canonical homomorphism from RV onto RV mod MV. Let fx be the minimal polynomial of theta over k, and let f bar of x equal to g1 bar x raised by e1 gr bar x raised by er be the factorization of f bar of x into a product of power of distinct irreducible polynomials over RV mod MV with each gix belonging to RVX modding. So far notations are concerned, we are just walking in a parallel lane to what Dedekind want. We are replacing Z by the valuation ring of a Krull valuation of any valuation, and we are replacing G bar x like to be the image, to be the polynomial coefficients in RV mod MV. Then he proved that Z theta is integrally closed. ZP theta is integrally closed. P does not, that can prove P does not divide AKs to Z theta. And my student Munish observed, reinterpreted it as saying that the ring ZP theta is P does not divide the index AKs to Z theta is same as saying that the ring ZP theta is integrally closed. And recall that ZP is the valuation ring of the periodic valuation. So Arsha proved that for any valuation ring RV theta is integrally closed, if and only for each I, one of the following conditions is satisfied. Either EI equal to 1, or whenever EI is greater than 1, then GV must have a smallest positive element V pi. And GI bar x does not divide M bar of x, where mx is the polynomial 1 over pi fx minus g1x raised by e1, grx raised by er, where what is pi? I didn't tell what is pi. Pi is V pi has the smallest valuation. There when we were in the periodic, here we had 1 over p because Vp equal to 1, that has the smallest valuation. So it's completely analogous to it. And of course, there the value group was Z, and Z has the smallest positive element here. And here, automatically, whenever EI is greater than 1, GB has the smallest positive element. And Arsha proved this generalized Dedekind criterion before we did. Actually, Munish and myself proved generalized it for discrete valuations, and I presented the paper in a conference held in Saskatoon, and Arsha was there, and I gave it an open problem that we want to extend it to a general valuation instead of a discrete valuation. And Arshad was smarter and more brilliant than us. Before we could do it, he did it and he published result. But he used very difficult ideas. He used model theory, which very few of us knew, and I never liked model theory. So we found a we kept on our efforts, Munish Kumar and myself, and we found another proof, and that another proof gave some other results also. The method of proof. Uh, uh, um, so so this is really Aisha. And this Munish Kumar, and I, I have shown this photo because this is the last conference I attended in person in March 2019 in Trivandrum. So using and I'm longing to attend a conference in person now. So using generalized Dedekind Criterion, we have given necessary and sufficient conditions involving A, B, Mn for RV theta to be integrally closed, where theta is the root of an irreducible trinomial fx equal to x to the power n plus a x to the power n plus b, not belonging to zx but belonging to RVX, where RV is any valuation ring. So next slide. And what did Jakhar and Sangwan proved in 2017 regarding this? Let V be a crude valuation of field K having valuation ring RV, maximal ideal FV, and a perfect residue field. We could not do without the residue field being perfect. So let P denote the characteristic of the residue field of RV mod MV in case it is positive. Otherwise the characteristic is 0. Let theta be a root of an irreducible trinomial fx equal to x to the power n plus a x to the power n plus b belong to RX, and let denote m1 n1 comma d, that means capital D is the discriminant of fx and denote is the GCD of m and n, and m1 remember was m upon d naught and n1 was n upon d naught. Assume that the valuation of d is positive, because if valuation of d is 0 we have nothing to do. Then all the factors, when we factor it modulo mv, all the factors will be simple. All the factors will be simple, and every EI will be 1, and RV theta will be automatically closed by generalized Dedekind criterion. So assume that valuation of D is positive, then RV theta is integrally closed if and only if the maximal ideal MV of RV is a principal ideal, say generated by pi, and the following conditions are satisfied. Number 1, when A and B both are in MV. Remember when we were dealing with prime numbers, when we were dealing with Z, then we said P divides both A and B. Then P square does not divide B. So VB equal to V pi, parallel condition. When A belongs to MB and B does not belong to MB, means when P divides A and P does not divide B, again we had the similar condition. And when P there it was P does not divide A and P divides B. Of course, to prove here is much more complicated, and to deal with integers is simpler. And then again we had and there is one case which did not exist, when ABM does not belong to MV, means P neither divides A nor B nor M. And they then V of C minus E equal to V pi, where C and E, as I showed before, are the intermediate terms in the expression for the discriminant of fx. So this yields a beautiful corollary. Let V, fx, and D be as in the above theorem with Vd greater than 0. Assume that the characteristic of RV mod M is 0. Things become very simple. Because in Z, when we consider the periodic valuation, the characteristic of the residue field is positive P. Then RV theta is integrally closed if and only if M is a principal ideal, say generated by pi, and either VB equal to V pi or V of AB equal to 0 and V of C minus E equal to V pi holds, where C and E are as before. So things become much simpler when characteristic of RV mod MV is 0. Now there may be more than one number theoretic application of theorem 1.6, but we in our paper published in 2018 gave one one beautiful application of theorem, this theorem, theorem which I just quoted, when is R with theta integrally closed. Now, number theories say that if K and L, we teach in the first course in algebraic number theory that if K and L are algebraic number fields with co-prime discriminants, then K and L are linearly disjoint on the field Q of rational numbers, and the value and the ring of integers of the composite field is the compositum of the rings of integers of the two fields AKL. The ring of integers of the composite field KL is the compositum of the two rings AKL. As an application of the previous theorem, we prove the following theorem, which proves the converse when one of K or L is a quadratic field and they are linearly disjoint from each other. So let K and L be algebraic number fields which are linearly disjoint over Q. If one of K or L is a quadratic field not containing the other, that means they are linearly. Of course, if one of them is a quadratic field, we have already assumed to be linearly disjoint. So if one of them is a quadratic field and AKAL is equal to AKL, the ring of algebraic integers of the compact of the composite field is the compositum of the two rings AK and AL. Of course, AKAL is always contained in AKL, but the composite being equal to the ring of algebraic integers of KL, that's important. So then the discriminants of K and L are co-prime. Then the discriminants must be co-prime. And how did we prove it? I'll hint a proof of it. Assume that L equal to, one of them was quadratic, so assume L equal to Q root D, where D is a quadratic field with D square for integers, set beta equal to 1 plus under root D by 2 or under root D, according as D is congruent to 1 mod 4 or D is not congruent to 1 mod 4. And we know that 1 comma beta is an integral basis of the field L. Let fx know the minimal polynomial of beta over q, and we know what is fx. Fx is either x square minus d or x square minus x plus 1 minus d over 4. Then al we know is z beta, means the 1 comma beta is an integral basis of L. Denote by ak the ring of algebraic integers of k. By hypothesis ak al is equal to ak al is equal to which we know is equal to r beta, is integrally closed because it is equal to AKL, because it is equal to, it is the ring of algebraic integers of the field KL, so it is integrally closed. And note that r beta is integrally closed if and only if so is the rp beta for each maximal ideal p of r. Since rp is the valuation ring of the periodic valuation of the field of the quotient field of R, Theorem 1.7 is applicable. Theorem 1.7 becomes applicable. So and it precisely tells us, because RP is the valuation. RP is a valuation, discrete valuation of the field K, of the field K. This theorem is applicable. Previous theorem is applicable, and for this it has been enough to prove that every prime which divides the discriminant of L remains unramified. Every prime which divides the discriminant of L remains unramified in K. That means that will prove that dk and dl are co-prime in view of Dedekind's discriminant theorem, which states that a prime P is ramified in an algebraic number field K0 if and only if it divides the discriminant of K0. And now to apply that theorem is not difficult, because fx is of the type x square plus ax plus b, where a either of this type or this, and it is a and b are known, and it's not difficult to apply it. Now the above theorem, the following problem arises from the last theorem. I've just stated and hinted its proof. Problem is let K and L be algebraic number fields which are linearly disjoint over Q. This problem has been haunting me for quite some time. If AKAL is equal to AL, AKL means the means the composite ring is integrally closed, then is it true that DK and DL are coprime? And I think I have a proof of it. I think I have a proof of it when we just said that one of them was a quadratic field. No, now I think I have a proof of it when one of them is a monogenic field. And what's a monogenic field is our next topic of discussion. So recall that an algebraic number field K is said to be monogenic if AK equal to Z alpha for some alpha. Otherwise, it is said to be non-monogenic. That is K has an integral basis which consists of powers of a single element. That is, K has a power basis. Dedekind was the first to give an example of a non-monogenic algebraic number field. He showed that the cubic field Q theta is not monogenic, where theta is a root of the irreducible polynomial x cube minus x square minus 2x minus 8 over Q. Dedekind in fact showed that there are three prime ideals of Q theta lying over the prime number 2. So by Dedekind's theorem on splitting of primes, the number 2 must divide AK is to Z alpha, the index AK is to Z alpha for each algebraic integer alpha generating the extension K over Q. And therefore this is not monogenic. This field this example works and this is not monogenic. Hasse raised the problem characterizing those algebraic number fields which are monogenic. And a lot of work has been done in this direction. And notation, let IK denote the greatest common divisor of the positive numbers AK is to Z alpha, AK is to Z theta, where theta runs over algebraic integers generating the extension K over Q. Note that K is not automatically non-monogenic if IK is greater than 1. The converse is not true. Is given in several examples, several books. The example is given K equal to Q root of 175 is not monogenic, but for this K, IK equal to 1. Excuse me.
You stop?
No, sorry.
Oh.
There was someone at the door. So theorem, and this is again by Dedekind, let K be an algebraic number field and P be a rational prime. For any number J, let P sub J denote the number of distinct prime ideals of AK lying above the prime P having residual degree J, and let N sub J denote the number of distinct monic irreducible polynomials over the field with P. FP is a field of degree J. Monic irreducible polynomials over the field FP of degree J, having degree J. Then P divides AK is to then P divides IK. IK is the called the index of an algebraic number field. So then P divides IK if and only if Pj is greater than Nj for some J. The above theorem is proved as theorem 4.35 in an elementary relative theorem of algebraic numbers by Narkevics. So, in 2022, my PhD students Anu Jakhar, former PhD student Anu Jakhar, and present PhD student Sumandeep Kaur proved the following: let K equal to Q theta be an algebraic number field with theta a root of an irreducible a trinomial of the type fx equal to x power 6 plus ax per m plus b belong to zx. Of course, naturally m will be less than or equal to 1 will be less than m less. Then K is non-monogenic if a and b plus 1 are both divisible by 8 or both divisible by 9. And of course they use this theorem of Dedekind, but they had to work to show the existence of a prime P for which divides ik, in both these cases. So monogenity of pure number fields. By pure number field of degree n, we mean a field q theta, where theta is a root of an irreducible polynomial x by n minus m belonging to zx. So Gal and Ramete, they are a student teacher team, but Ramete now is the faculty. So they proved in 2017 the following result: let m equal to r plus 16k be a square free integer with k belonging to z. The field k equal to q m raised by 1 over 4, the fourth degree pure field, is monogenic for r equal to when r equal to 2, 3, 6, 7, 10, 11, 14, 15, and is non-monogenic when r equal to 1, 5, 13, with the exception of q cube fourth root of -3, which is monogenic. So this covers all the possibilities because m has to be square free. There are no other possibilities for r, and they conjectured that for m equal to 9 plus 16k square free, the only monogenic fields are q fourth root of 73 and q fourth root of 83. And in 2017, in a paper which appeared in Journal of Number Theory, they proved that let m equal to r plus 36k be a square free integer k belongs to z, the field k equal to q m raised by 1 over 6 is monogenic for these values of r and is non-monogenic. And this completely exhausts all cases because keeping in mind that m has to be square free. So and in the same paper, they proved let m equal to r plus 64k be a square free integer, give the field k equal to q m raised by 1 over 8 is monogenic for these values of r and is non-monogenic for these values of r, with the exception of q cube root of -3, which is monogenic. And their conjecture is that the minimal index of, I didn't define the minimal index, algebraic number theories know it, that it is the minimum of all the indices of ak is to z alpha, where alpha runs over generators of k over q belonging to algebraic indices. The minimal index of this is 16. So these are the references. Parents reference comes first because I used parents criterion, and Selmer because I used the irreducibility of the polynomial x raised by n minus x minus 1, and Swan for the discriminant formula for a general trinomial, and Uchida, of course, is the backbone of the whole work, which instigated when is z alpha the ring of integers. That is why I have named the title of my lecture after Uchida's paper. That paper inspired me so much, written in very simple language. When is z alpha the ring of integers, which appeared in Osaka General Mass. I could not, by the way, find from internet photo of Uchida because I put everybody's photo except for Uchida's. And the first time I read a proof of Dedekind Criterion was from Henry Cohn's course in computational algebraic number 3. The first time I read a proof of it is in this Dedekind. Of course, now my student Anu Jakhar and myself, we gave very simple proof of Dedekind Criterion, and that too for arbitrary rings. So, of course, the Bible is always there, Narkevich's book, Elementary and Analytic Theory of Algebraic Numbers, and Arshav's proof of Dedekind Criterion, and Munish Kumar Dedekind Criterion, and he also proved some other very significant result. Munish Kumar in his long paper, and this is the result, Jhorar's result, which began this problem. And this is that on prime divisors is the index of the algebraic integer, and this is when is r with theta integrally closed, when theta is the root of a trinomial, characterization of prime dividing the index of an algebraic integer, and Gall and Ramete papers. Gall's book is worth mentioning. Diophantine equations and power integral basis Theoretic algorithm, second edition. It appeared in 2019. It deals with monogenic fields. This is our latest and newest proof of Dedekind Criterion. A note of Dedekind Criterion, it just uses basic algebra of MSc class. So it appeared in 2021, and this is Jakhar and Sandeep's paper, which give two classes of non-monogenic sextic fields. And this is my book, a textbook of algebraic number theory, which has just appeared. According to the records, they said it was published on 27th of April, 2020. But I have yet to get it because I have not yet seen the book myself, except its e-copy. And this book contains a section this book contains appendix on field theory, and that appendix on field theory contains a section on valuations, and which are it contains a section on valuations, and which relate discrete valuation ring with discrete valuations. It's a small, very small section. And this book is dedicated to my teacher, Professor Bamba, who taught me algebraic number theory when I was in MSc, and this book is dedicated to him. And this is his latest photograph. Thank you for your attention.
Hello. Have you considered other polynomials other than trinomials, or somebody else has considered?
Pardon?
Polynomials other than trinomials for this problem?
Yes, my student Anuj wrote a paper on quadrinomials also, but the results on quadrinomial are not complete. We have not taken any condition on A and B. For us, A and B are general, just x to the power n plus x to the power m is irreducible. But when he does it, he takes some conditions on A. He has published a paper in Rocky Mountain Journal, and he has taken some conditions on A, B, C also. There C, because it's a quadrinomial, there is C also.
Okay, thank you. Yeah. Nice talk. Very nice talk.
Are there other questions?
Yes, sir.
Yeah, can you hear me?
You're muted.
Yes.
Unmute.
No, I have unmuted.
Yes, sir.
No, it's a beautiful talk. I can only tell you that in 1965, February or March, I spent a week thinking about this problem.
Which problem, sir?
That when are the algebraic, the global fields, when are they monogenic?
Okay. All global fields.
No. Yeah, I just wondered whether that was a natural question. And I spent a week thinking about it. Nobody told me any literature. So I would have been very happy if your book were available at that time.
Sir, my book does not give any, only gives definition of a monogenic field. It doesn't give, it doesn't tell these results. So Gall and Ramete's book gives a lot of Gall and Ramete's.
I'm just telling you that in 1965, February or March, I spent a week on this problem. But I could not get anywhere.
No, Gall and Ramete,
Yes.
Gall's book, their book gives a lot of information on monogenic fields. I only the example given by Dedekind, I only give explanation for it why the field is not monogenic, and I also prove why the index of the field Q cube root of 175 is 1, and I also give some exercises telling them similar exercises that the index is 1 but the field is not monogenic, and I give hints for that. So my in the book I'm limited only to that.
Okay. Okay. Thank you. Thank you. Yeah, very nice talk. Thank you.
Thank you.
Thank
For
you very much.
Khanduja, I mean,
Professor
just a
Khanduja.
non-technical question. Can you go back to the previous 2 slides, the last theorem?
One slide. This one?
Yeah, no, I mean the results before that.
Okay.
Yeah, just before this. Yeah.
Yes.
Yeah. Okay. Actually, I'm an outsider to this, but I mean, the values of R, where it is monogenic and where it's not, in both these theorems, does the order, I mean, do you see some order which corresponds to some order that we encounter somewhere else in mathematics?
I think the
Like in Sharkovsky's theorem on,
36. R is modulo 36.
on period 3,
something like that
in
must be
case
there
theory.
to find
So,
cycling.
is there some recognizable pattern in the distribution of these R's where they are monogenic and where they are not?
Actually, neither me nor the authors would identify any pattern. Maybe somebody with knowledge in some other area can identify a pattern.
Well, that would be great. I mean, in case it does. I was trying to recollect, this Sharkovsky's theorem, about period of about 3 being the basic period for continuous functions on intervals. So the order is of integers, once a function has a period, continuous function has period 3, then it has all the orders. It has points of every other order.
The period 3 is occurring not always, but quite often. I can see that.
No, that period 3 is, that is the beginning. Once you have period 3, then you have everywhere. Yeah, it doesn't always occur, but once it occurs, then all the periods occur. So the ordering that he devises is, out of this world. He orders the odd integers first, then multiplies them by 2, and then powers of 2 in an increasing order. So there is no complete order over there, but then it tells us, which period follows which period. And I was trying to find out maybe that order is there, but there should be some order which we may perhaps encounter elsewhere in some other domain of mathematics. So that would be really great.
It may be related to squares, cube, etc. Modulo 36 or 64.
Kulkarni sir, I can send you the PDF of ebook of Professor Gal.